Hello and welcome back to the channel. It's Mark from PowerSonic and Apprentice 121. Today we're going to have a look at some Ze and PFC testing. And that's because a number of learners have been getting in touch with me saying how they're not getting any experience of this in their training environments. Now I have to say that that is largely those in private training establishments, generally on the full-time study routes doing level 2 and level 3. They then get packed off to go and do their portfolios, and after that their AM2s. And in the blend of all of that, they've had very little experience of doing live testing. The general excuses provided, and I will call them excuses because that's what I think they are, is that it's in breach of the Electricity at Work Regulations 1989 because other methods are available. There is elements of truth in that, but largely speaking, it's nonsense. For those of you who are out doing vocational training, you will be lucky enough to be amongst generally FE training providers who still deliver that very important live testing training in the classroom, and also among employers who will be delivering elements of the training with you out on site as well. So I wanted to cover a little bit of that off in this content, and I do want to say this isn't instructional. It will not replace that training. You need to find an electrician to work alongside and show you all of this in person, and you need to go through those proper training routes. For full disclosure, I will have bad practices. This might not align with the intent of the syllabus that you'll be shown and delivered through that training provider when actually done, but I wanted to do something because you can't just sit in silence about all of this forever. And yeah, that is what this video is about. At the moment, this is isolated. I'm very lucky to have lots of isolation points within this simulated training environment. And while we get people coming in here to receive that from me in person, in those safe conditions, I think we can do a little bit more through the content. So first up, I guess, why do we even need to do ZE testing and the PFC testing? And largely it's to do with design. So if you do an inquiry for your ZE measurement from your energy supplier on a single phase system, TNCS, generally they will come back with 0.35 because that's the maximum allowable. And then when you run through your design, it may not cause you a problem because there's quite a wide tolerance in general to the circuit division using B-type breakers where they have those larger maximum ZS values. So that's kind of where this is structured. However, in a commercial environment, it could be that you're using fuses or D-type breakers where those values are much smaller because of that. So you could be down at 0.2 something, or even lower when you're talking distribution circuits. So obtaining a measured value of ZE can become really, really important. In terms of the PFC and PSC, they're two different things but result in the same answer, if you like. We're looking for the maximum fault current that can exist in our installation, and that's so that we select the right circuit protective devices. Lots of these will carry markings of 6, 10 and 15 kA rated values. That's the maximum fault current they can withstand for your typical RCBOs and MCBs. To step above that, you're looking at fuses and your MCCBs where they can carry much larger fault currents. And that's why you'll find those at main intakes on larger systems in panel boards. They've been selected for that reason, along with the current that it'll allow it to carry during normal operation. So if you get those large fault currents, because you've got a low impedance loop back to the transformer on those large suppliers, your overcurrent protected devices can withstand them in the worst case circumstances. When you're further into those installations, you can then revert back to protective measures such as a 10 kA rated overcurrent protected device, because the fault current, the maximum short circuit current at that point of utilization, so those sub-distribution boards, is much lower, and you have those protected devices further towards the source of the installation that are rated for the fault currents that they might encounter in those positions as well. So it's not a case of if you've got, say, 11 kA maximum short circuit current at the intake that you have to use that throughout the whole installation. It's just the point where you're putting your switchgear, basically. So it's all to do with adequate design and ensuring your overcurrent protected devices can operate in terms of the maximum loop impedances they might have on those circuits, and also to the maximum current they might encounter due to short circuit in the worst case circumstances. So I hope that's helpful. I would say if you want to go into delve into the theory and the technicalities of it all and the calculations, there are lots of them to use around all of this, where you'll start seeing the square root of 3 a fair bit. That's one of the things I often remember in my times in the classroom. But go off and look at Joe Robinson's training, GSH eFix, I think they've got stuff on all this as well. And there's a great channel from Craig O'Neill called Completely Electrical, which is out there too. He's now a technical manager at the IET, and I think he goes into all of this in quite a bigger depth as well. So if you're interested in the science and principles and all the calculations underneath all of this, go off and check it out. I'm just going to show you how to actually carry out the test, why those values are important, and why it's good practice for electricians of the future to be given the skills they need. You know, we're all on about skills shortages and, you know, the problems we've got out in industry. A lot of that traces back to really poor training of people on full-time study routes. We see 70% of trainees drop out anyway, and the ones that come through aren't given that high quality training that they should be getting due to all the funding that's around that type of thing. Lots of these are school leavers, lots of them are taxpayer funded, and they're just not getting it. Greedy training providers taking money out of industry and de-skilling. And some of those who've come forward to me with complaints about all of this are training with some very active providers on social media, and it's been really tempting to call them out, I have to say. However, that's not my style. I don't really have the time or inclination to do it. But yeah, I see you. Let's move on with the video. So you will have just seen me opening that distribution board. The power was off. If I scroll down, be able to see we've got this isolation point here. It is in the off position, so we're able to do that without any energy leading up to this board. The look of having a training environment. Now you can see I popped a little clamp meter on here, and if we look at that as it is, I'll bring you in a little bit closer just in case that's not coming over on camera. We have got no leakage current running through that earth. Now this is a check you might want to make before you disconnect your earth, main earth, or bonds for that matter, from an earthing system. So any kind of deconstruction of the earthing system, you want to make sure that there is no current flowing in it. Now we wouldn't expect to have any presently because there is no electrical energy. If I step you back just a little bit, we can pop that power back into the on position, and if we chuck the light on in there again, we can still see, you can see that on camera, but again, zero. So we've got absolutely nothing flowing in there. And again, I would anticipate that because there is nothing on the final circuits. So now we can look at this in terms of our G38 probes. So as you'll see here, I've got a voltage indicator, and we've got our shrouds over the end to just expose the 2 mil there on the end. There's this option here in the 859 where you've got those retractable tips. So again, it's going to be very difficult to come into contact with those while you are carrying out your test measurements. And with the MFT, as we're demonstrating in this video, again, we've got our GS38 probes with guards. So with this, it's important your fingers never go past those guards, and you need to inspect your leads for any frays, any damage to the probe as well, to make sure that they're in suitable condition, because these are live tests and you want to be absolutely sure they're okay. Another test you can do with your in terms of your earth before you disconnect it, so you can use a contact voltage indicator, and this, we're lucky enough to have the ability to do that with this 859. So if I probe onto the earth there, we can see there's no voltage on the neutral, but as I go onto the lines, it starts to get a little bit upset because there's voltage there. So we've got that switch in the on position now below this board. And again, we've got the guards on here. We've got a really long probe, so I'm a long way from these terminals, and I have no problem probing on there and seeing that there is voltage. But if we've got anything above 50 volts on these, it will start to get upset. And that's the same on, I think this voltage indicator does that as well. We'll have a little check of that one. So this one is the TIS 8000. And I think again, if we're on AC and we start probing around, yeah, again, it's getting upset because there's voltage there. If we're on the earth, the neutral, it's not bothered. Bring that up there. But as soon as we go onto a live terminal, it's letting us know that we've got voltage there. So fantastic. We know we're in a safe state to disconnect this earth and carry out our ZE measurements, or as it is in this case, ZDB. I'm going to call it ZE in this video just for the purpose of the exercise, but we know it's not. So as we've discussed, we've got RCDs in advance of this, so we are going to have to do this on the no trip setting. and we are now going to be recording. We're going to call it ZE. This is actually ZDB because it's a subboard, but we'll pretend it's a main intake and we'll just approach it in that instance. The figures will be a little bit higher than you would find at a traditional intake. You'd be probably down in single 0.089, whatever. You could be up as high as 0.35. Generally, it's much lower than that on a TNCS. Now, if we go about doing this test, first up, we're going to probe onto the L1 phase. Again, with our GS38 probe. I need to remember to pop the power on because I disconnected that earth with it off. And you can see we've got 242 volts. If we hit that test button, it will run through and give us a measurement based on the L1 phase. And we're looking for this box here. So this is our LPE Z value. And that's the loop impedance between the line and the earth path. And you can see we've got 0.38 on the L1 phase. If we go to the L2 phase now, we can hit that test button again. And with these tests, we're looking for the highest value. That's the one we would record and use for our design purposes to make sure the overcurrent protected devices would operate. I can see there it's just thinking about the test result again. We've got 0.34, so that keeps 0.38 as our highest value so far. In the last phase of L3, we can repeat that test and see what we get. Again, fingers behind the guards, GS38 probes, a glove on for some extra safety, and we should get a value accordingly in 1 second. Here we go, 0.46. So that one's considerably the highest value so far. So we've got our 0.46, and that's the one we would record on our test sheets, and the design value if you were approaching this pre-doing any work, so you want a figure to work from when you're speccing all your overcurrent protective devices. So let's dive in and have a look at how we carry out this PSC, PFC measurement. As we've discussed, we've had to reconnect the earth back into the earth bar, as you can see over there behind me. I'll take you in a little bit closer while we carry out the test. And we've also got a clip onto the neutral bar. We've energized the board because this is, again, a live test, and I've got my PPE in position as well. We only really need to be using the one probe with this kind of test. We need to put the instrument into the right mode. I'll bring you in closer when we do all of that, and then just work through and record these values. There are some calculations you can use to come up with figures for all of this as well, and they are detailed in some technical articles on the internet, and there are also some stuff on Joe Robinson's channel as well. He's covered this before, I remember watching them, and Craig O'Neill on the Completely Electrical channel. But as for carrying out the actual tests, we're going to go into this and we'll talk about some of the rule of thumb and how this instrument can help us actually take direct measurement. So hopefully I'm in position there where you can all see what's going on. It is hard to get this to focus on the right things as I move around, so apologies, and I will reference the numbers that we're measuring just in case they don't come up as clearly as they should. But if we go back into the home menu, we need to be on our loop measurement. Now, as I've discussed earlier on in this video, there are RCDs on this circuit that are pre this board, so we have to do this on the no trip setting. So you can see I'm in there, we're on no trip, we're on our line and neutral for this one in the standard condition. If we click tick, and it's going to take that measurement between line and neutral in this case. Now obviously the RCD aspect doesn't really matter because we've not got an RCD that's going to be affected with tests through the line and the neutral. However, when we come to do the line and the protective earth or earth, then we will have a problem with the RCDs and it'll adjust accordingly. But if we go through and carry out these tests, I'm going to probe in onto L1, and you should see we start to get a measurement. And again, these are the GS38 probes, and my fingers are behind the guards, and they are gloved up. If I hit test, it will now carry out the ISC value, and you can see we've got 396 ohms, and that's the LN value. Sorry, amps, not ohms. If we repeat that test, you can see we've got a bit higher voltage on the L2 phase at 247 volts, and it's going to carry out that test again, and we've got a little bit higher current at 403 amps. You can see this Z value here, that's the impedance value between the line and neutral path. This is a TNCS supply, so it should be relatively consistent with the earth as well. If we go on to L3, make sure we're getting a good contact again with that GS38 probe. It is a bit tricky with some of these onto the screw heads. You need to make sure you get in there. And we've got 433 amps. Now with that, you can double this figure, and that would be a good rule of thumb for the 3-phase maximum short circuit current you would see. So if we doubled that, you know, we're near enough around 900 amps, 866 to work out precisely. It will fluctuate depending on the supply voltage at the time you carry out the test, but that is a good value. We'll speak about why we need that later on in the video. So I've just had a little reposition of the camera because I'm not sure if that last clip was fully picked up, but we'll cross our fingers. I've changed the instrument over now back to no trip. You can do it just LPE and it won't have an RCD in circuit to upset, and that's the high current test, but we need to do this in the low current test, so the no trip. It's supposedly not as accurate, however it's an acceptable way of gathering the test result. If RCDs are there, they are there. So generally speaking, at a main intake you're unlikely to have an RCD pre your distribution board unless it's maybe a TT install. However, this is a simulated training environment. We've got RCDs in lots of places for safety over function in that application. You can see here we've got around 243 volts between line and neutral and line and protective earth, which is what we want. So we can hit test, and this is going to give us values between the line and neutral loop and line and protective earth loop, and it will also give us our PSC, so the line and neutral short circuit, and the PFC, the line and earth short circuit. And you can see we've got 317 amps on the PSC, so that's your line and neutral, and 306 on the PFC, that's your line and protective earth. We can go off now and repeat that test on the L2 phase. So again, probing on, voltage on this one is a little bit higher, and it will vary across your 3 phases. They're usually pretty close, but it depends on the local network conditions, the time of day. These things all fluctuate. So we're looking at this this particular point in time across the 3 phases, and you can see here we've got a PFC of 499 amps on the line and protective earth, and we've got, whoops, I've just lost that. It was less anyway on the short circuit side for the LN loop, or the LN, so your PSC. So if we go through that test again on the L3 phase, you can see we will receive different results again. It will vary depending on which one we're using. And you can see here we've got 356 amps for our PFC and 336 amps for our PSC. If you're unsure what those are, go off onto Google, other YouTube videos, and dive into that at technical level. I'm just going to repeat that L2 phase test, make sure I've got my probe on there nice and tight. Sometimes with your GS38 probes, you maybe don't hit the screw head bang on, and it can impact your results. So if you get something that looks a little bit off, repeat the test just to ensure you're getting the correct value, and the instrument's just running through that there. And you can see we are on our L2 phase, we're getting 514 amps as our PFC. So to get the maximum short circuit current, you would double that value for the rule of thumb, which would give us just over 1,000 amps as our maximum short circuit current on this particular installation. Now with this test set, we can actually do an LL test. So that's where you go between the phases to measure those maximum values rather than doubling by rule of thumb. So I will set out the instrument and we'll run through that test in just a sec. So this one is a little bit more tricky because we've got 2 probes in my hand, and I would generally be using my test instrument, my test lead with the button on to trigger the test. However, some other people had said on prior content that they don't have those, and how do you do the test without them? So this is why we're demonstrating this way around. You can see we've got 423 volts between L1 and L2. We can carry out that test and it will give us our short circuit current between those 2 phases, and we've got 724 amps. If we go in now, we can also probe in onto L2 and L3. If I go back to the main menu, make sure we're getting those in nice and tight. We've got 426 volts there. And carry out this test again. And you can see we're getting 737 amps. And then lastly, if we probe in, again with the one glove, this is quite tricky, but I need the other hand to work the camera, so it's a bit awkward. We've got 422 volts, again, fingers behind the guards, applying some pressure, and we've got 750 amps. Now there is a calculation that you can use with that rule of thumb. It's the doubling is accurate, it's not so crass as to be miles out, but it does go on to the side of caution, and you can see that that is a value above what we've measured here. However, for those of you who are interested, I have recorded some content which has gone on Instagram, LinkedIn and Twitter doing this same process again, and those figures were much more closely aligned than they are now. So we had around 1,000 amps for our doubling rule of thumb, and you can see we've got, I think it's about 750. I think that is the maximum one we've recorded. So there is a bit of a difference there, and there is the calculation. I think it's where it has the square root of 3 in there somewhere as well, but it's not as simple as applying the square root of 3 multiplied by the figure that you've actually recorded. There's something else you need to do in there as well. Like I say, I'm not a bookworm. I'm not great at maths and calculations. Joe Robinson, Craig O'Neill, Completely Electrical, Joe Robinson Training. Check those guys out. They've got content galore on that. But it will explain why there is a subtle difference there. I am going to repeat again this 3 lead test. I can pop the probe back on just once more on that L2 phase, because it was very, very high in comparison to the others. And it could be entirely normal. It could be something weird that was going on at the time I carried out the test. So I'm just going to repeat it again, third time lucky, just to see where we're at. And again, because this is a low current test, it takes a little bit longer, and we'll see what value it comes back with. And you can see again, we have actually got that 546. So there's something going on the L2 phase to make that be the case on the local network. So it's interesting how that plays out. So you can see that I've popped the cover back on. We've now got all of those live parts fully enclosed. This switch is still in the off position, and I've turned the test instrument off as well. Don't want to be wasting that battery power. I hope that's been of some use. If you've got any questions, do drop them in below. If you're an electrician and you approach this differently, share them in the comments as well. It may help a learner or two out in their development. I'm not an expert in this. I probably have my own real bad habits and showing some bad working practices through the course of this video. I will tie on to the end of this the video I shared in the worlds of Instagram, LinkedIn, Twitter. I think that's the only places I've shared it so far, because that was done a different day and I've probably forgotten certain aspects that aren't in this and are in this, if that makes sense, and the two tied together might just help. So it is pretty much a repeat of the same content you will have just watched. If you want another run through it in short format, we'll tie this on at the end of this one. Otherwise, if you've got any more wider comments about some of the gear, or you've got any questions about the test instruments or whatever else, drop them in below as well. If you haven't already, don't forget to subscribe to the channel. And as you'll see, it's absolutely Baltic in here. I don't know if you could see my breath coming through on camera, but it is freezing. It's about -4 outside. So I'm going to dive back into the warm office space and edit this video up. And otherwise, I'll see you on the next one.